We are given a vector field and along an ellipse x square by 16 plus y square by 9 equal to 1 and along the xy plane, so z equal to 0. So we want to determine the work done by this vector field. Can we do it? Of course, yes. There are many methods for doing it. So one of them being is by applying Stokes theorem. So let us apply Stokes theorem. Once again, f is given to be 3x minus 4y plus 2z times I plus 4x plus 2y minus 3z square times z plus 2xz minus 4y square plus z times k. Now, if we want to determine the work done by using Stokes theorem, so we need to determine curl of f. Curl of f is given by ijk, by this determinant ijk, let's say determinant rather, del del x, del del y, del del z, x component of, I component of the field, j component of the field, and k component of field. So let us determine I component. I component is given by del del y of 2xz minus 4y square plus z. Once again, del del y of 2xz minus 4y square plus z. Del del y of 2xz is 0. So del del y of minus 4y square only, because del del z of y is also 0. Del del y of z is also 0. Minus del del z of 4x obviously 0, 2y also 0, minus 3z square. When we are differentiating partially with respect to z, we will treat x and y to be constant, and derivative of constant is 0. So that's the I component. What about j component? Minus del del x of 2xz, del del x of 2xz, but del del x of minus 4y square is 0, del del x of z is also 0. Yes, j component. So del del x of 2xz and del del x of minus 4y square is 0, del del x of z is also 0. Minus del del z of, we are computing j component, so del del z of 3x is 0, minus 4y is also 0, 2z. So we are computing j component. Lastly, let's compute k component. If we want to compute k component, then we find del del x of plus del del x of, we want to compute k component, del del x of 4x, and then del del x of 2y is 0, del del x of minus 3z square is also 0, minus del del y of 3x is 0, minus 4y, it will survive, and 2z is also 0. Okay, let's determine it. Del del y of minus 4y square is minus 8y. Del del z of minus 3z square is minus plus 6z times I minus, let's evaluate the j component, del del x of 2xz is simply 2z, del del z of 2z is simply 2. Lastly, let's evaluate k component, plus del del x of 4x is 4, minus minus plus, del del y of plus 4y is 4. So we have computed curl of f to be minus 8y plus 6z times I plus of 2 2 minus 2z times j plus 8k. Now, we want to determine curl of f dot n ds, where n is unit normal to the surface. The surface is in the xy plane corresponding to z equal to 0. So unit normal is simply k. So unit normal is simply k vector. Therefore, f dot n equal to minus 8y plus 6z times I plus 2 minus 2z times j plus 8k dot k. And I dot k is 0, j dot k is 0, k dot k is 1, so this is simply equal to 8. Let us recall the formula based on Stokes theorem. Integral over closed curve f dot dr equal to integral over surface f dot n ds. But integral over closed curve f dot dr is simply work done. Work done is nothing but integral over closed curve f dot dr. In this case, where closed curve is the one round of the ellipse. So we don't have to evaluate this. We should evaluate integral over surface. Now surface is in this case is nothing but the region bounded by the ellipse. Let R denote region bounded by the ellipse. F dot n we have just computed. F dot n turns out to be simply 8. And ds, that's the region by the bounded by the ellipse. So dx dy. Now 8 being a constant, we can take it out of the integral. Now region, if you integrate it, you will simply get the area of the ellipse. If you integrate any constant function over a region, then you get the area of the region. So we get the area of ellipse. But we know that area enclosed by the ellipse x square by a square plus y square by b square equal to 1 is given by simply pi into a into b. Pi times semi-major axis times semi-minor axis. In this case, we are given ellipse to be x square by 4 square plus y square by 3 square equal to 1. Therefore, work done is simply equal to 8 times area of ellipse, area 8 times pi into 4 into 3. That's equal to 96 pi units.